Now, we are given a table with 4 different KSP values, but you should be careful. The KSP value for a compound is not the same thing as the solubility of that compound. And each of these compounds does contain silver in its formula, but be careful, notice that each formula does not have the same ratio of cations to anions. Welcome to AP Chemistry Review and Practice. My name is Michael Farabaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 7.11 and 7.12. As you can see on this slide, these topics fall under Unit 7 in the AP Chemistry curriculum, Equilibrium. You can add your comments and questions below this video, and you can also email me with your comments and questions at apchemistryreviewandpractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now let's move on to the review for topic 7.11, Introduction to Solubility Equilibria. Here are some essential knowledge statements from the AP Chemistry course and exam description. The dissolution of a salt is a reversible process whose extent can be described by KSP, the solubility product constant. The solubility of a substance can be calculated from the KSP for the dissolution process. This relationship can also be used to predict the relative solubility of different substances. The solubility rules can be quantitatively related to KSP, in which KSP values that are greater than 1 correspond to soluble salts. See the essential knowledge statement from topic 4.7, Types of Chemical Reactions, shown below. Precipitation reactions frequently involve mixing ions in aqueous solution to produce insoluble or sparingly soluble ionic compounds. All sodium, potassium, ammonium, and nitrate salts are soluble in water. And the molar solubility of 1 or more species in a saturated solution can be used to calculate the KSP of a substance. Now let's move on to the practice for topic 7.11. This is question 1. In question 1, we are given a balanced chemical equation, and it says lead Roman numeral 2 bromide, which has the chemical formula PbBr2, is slightly soluble in water and dissociates according to the equation given above. A chemist prepares a saturated solution by adding excess solid lead 2 bromide to distilled water and stirring until no more solid dissolves. So in part A of this question, we have to write the expression for the equilibrium constant, KSP, for PbBr2. Now, in an earlier episode of AP Chemistry Review and Practice, this was from episode 20 that included topic 7.3, reaction quotient and equilibrium constant. You can see highlighted at the bottom of this slide, it says that the reaction quotient, also the equilibrium constant expression, does not include substances whose concentrations or partial pressures are independent of the amount, such as for solids and pure liquids. So we do not include solids or pure liquids in either the reaction quotient or the equilibrium constant expression. Now, in episode 20 of AP Chemistry Review and Practice, I had presented an example of the dissociation of calcium fluoride. Again, it says KSP, but it says a student wrote the following expression. Now, one of the mistakes that the student had made was that they had neglected to include the charges on the calcium ion and the fluoride ion. And then another mistake was that they had incorrectly included the solid calcium fluoride in the KSP expression. So in that episode, I showed you that the correct answer for the KSP of calcium fluoride would be concentration of the calcium ion with its charge times the concentration of the fluoride ion with its charge, and then it's squared, and that's because there is a coefficient of 2 next to the fluoride in the balanced equation. So we're going to see a similar type of setup for, back to this particular packet from this episode, the PbBr2. We have a solid on the left, we have the lead ion and the bromide ion on the right, and the bromide ion has a coefficient of 2. So here is the correct answer to part A of question 1. Again, that's very similar to what I had shown you in an earlier episode of AP Chemistry Review and Practice. So I did not include the solid lead bromide in this expression. Now, moving on to part B of this question, we are given the solubility in units of grams per liter. It says the chemist determines that the solubility of this lead bromide compound is 4.34 grams per liter at 25 degrees Celsius. So in part I of part B, we have to calculate the molarity of each of the following ions in the saturated solution of lead bromide. Now that would be the concentration of the lead ion, the concentration of the bromide ion in units of moles per liter. So since we have molarity in part BI, but we are given the solubility in units of grams per liter, then we will need to convert from grams to moles using the information from the periodic table. So what I did is I calculated the molar mass of PbBr2, and that worked out to be 207.2 for lead plus 79.90 for bromine times 2, and I got 367 grams per mole for the molar mass. Now I will start with 4.34 grams per liter. That's 4.34 grams of PbBr2 for every 1 liter of solution. I'm going to put 1 mole on top and the molar mass on the bottom in grams. And when I do that math, 4.34 divided by 367, this is what I got on my calculator, and I will round this off to 3 significant figures. So that would be 0.0118, and the units are moles per liter. So that's the molarity of the lead bromide. Now, does that mean that 0.0118 is going to be the concentration of both the lead ion and the bromide ion? No, not necessarily. Let's go ahead and take a look at the coefficients in this balanced chemical equation. So we can see that the coefficients from left to right are 1, 1, and 2. And so if I have 0.0118 moles of PbBr2, well, that would be 0.0118 moles for the lead ion. So that is the concentration of the lead 2 plus ion. But that 2 next to the bromide means that for every 1 mole of the lead ion, there should be twice as much. There should be 2 moles of bromide for every 1 mole of lead. So what I did is I took 0.0118 and I multiplied by 2. And when I did that math, I got 0.0236. So that number, 0.0236 moles per liter, would be the concentration of the bromide ion. So we're almost done with question 1. We have come up with the KSP expression for part A. And then in part BI, we have converted grams per liter for the saturated solution of lead bromide into moles per liter for each ion. So now let's go ahead and finish off part B. It says in part BI, calculate the value of KSP for PbBr2. And now that we know the answer to part BI, and we can take our answer to part A, let's simply plug in these values and do the math. So it's going to be concentration of lead times concentration of bromide squared. So this is what I put into my calculator, 0.0118 times 0.0236 squared. And when I did that math, I got my answer to part BI, calculating the value of KSP for PbBr2. I got 6.57 times 10 to the negative 6, and equilibrium constants do not have any units, so that's why this answer is correct with just a number, and there are no units for an equilibrium constant. All right, well, these are the answers to parts A and B of question 1. Now let's take a look at question 2, which is a multiple choice question. In question 2, it says, based on the KSP values in the table above, a saturated solution of which of the following compounds has the highest concentration of silver ions? Now, we are given a table with 4 different KSP values, but you should be careful. The KSP value for a compound is not the same thing as the solubility of that compound. And each of these compounds does contain silver in its formula, but be careful, notice that each formula does not have the same ratio of cations to anions. So the first 2 formulas in this table are silver chloride, AgCl, and silver bromide, AgBr. Now for these compounds, there is a 1-to-1 mole ratio of cations to anions. But in the next 2 formulas in this table, silver carbonate, Ag2CO3, and silver chromate, Ag2CrO4, those compounds have a 2-to-1 mole ratio of cations to anions. And so it turns out that the math we need to do is actually different when it's a 1-to-1 ratio versus a 2-to-1 ratio for cations to anions. The calculation, the setup, the math is different. So before I do any actual setups for calculations, I'm going to eliminate 2 of the 4 choices in question 2 by a simple comparison of the KSP values. So I'll start with choices A and B. I'm looking for the highest concentration of silver for the correct answer to question 2. And so by starting with choices A and B, I'm comparing the KSP for AgCl, which is 1.8 times 10 to the negative 10, with the KSP for silver bromide, AgBr, which happens to be 5.4 times 10 to the negative 13. Note that when you are comparing the KSP values of 2 salts with the same ratio of cations to anions, then a higher KSP value does mean a higher solubility. So by comparing 1.8 times 10 to the negative 10 with 5.4 times 10 to the negative 13, I'm going to go ahead and eliminate choice B. So because we're looking for a higher concentration of silver, then I will choose AgCl as a comparison because it's the higher KSP value. It doesn't mean that choice A is the correct answer to question 2, but I can definitely eliminate choice B by going with the higher KSP value. Now I'm going to do a similar comparison for choices C and D. So that would be when comparing the KSP values of 2 salts with the same ratio of cations to anions, I can see that 8.5 times 10 to the negative 12 is larger than 1.1 times 10 to the negative 12. That means I will go ahead and eliminate choice D, choosing the higher KSP value. So I've now narrowed it down to either choice A or choice C. But as I mentioned, the math is different when you have a 1-to-1 ratio versus when you have a 2-to-1 ratio. Let's go ahead and start with choice A. So now I'm going to begin to do actual calculation setups. There is a 1-to-1 ratio, so the concentration of silver would be represented as an unknown variable. That would be X. And the concentration of chloride is the same as the concentration of silver based on that 1-to-1 ratio. So if the KSP equals X times X, or X squared, I will pick up my calculator and solve for the concentration of the silver ion in a saturated solution by doing the square root of this KSP. So the square root of 1.8 times 10 to the negative 10 gives me 1.3 times 10 to the negative 5. So that number, 1.3 times 10 to the negative 5, that would be the concentration of silver in a saturated solution of silver chloride. Now, moving on to choice C, again, we have a 2-to-1 ratio. So it's not going to be X times X, or X squared times X. It's actually 2X quantity squared times X, and that's 4X cubed. Now, if you're looking at that setup for the calculation, and you're wondering, why is the concentration of silver written as 2X? It's because of the stoichiometry from the balanced chemical equation. So for every X moles of silver carbonate that dissolves in water, we would get X moles of carbonate ions, but we would get 2X for the number of moles of silver ions. So hopefully you can see that the setup to solve for x would be 2x quantity squared times x, which is 4x cubed. Well, now I have to do the math, but you can see I'm not simply taking the square root of the KSP, which is what I had done for choice A. So I'm going to take the KSP, which is 8.5 times 10 to the negative 12. I will divide by 4, and then I have to take the cube root to solve for x. So when I pick up my calculator, it's going to be 8.5 times 10 to the negative 12 divided by 4. And then when I take the cube root of that number, I get 1.3 times 10 to the negative 4 moles per liter. Now, that is x. So that's the concentration of the carbonate ion in a saturated solution of silver carbonate. What about the concentration of silver? Well, that would be twice as much. That would be 2x. So you can see 1.3 times 10 to the negative 4 times 2 is 2.6 times 10 to the negative 4 moles per liter for the concentration of the silver ion. Now, go ahead and take a look at the correct answer to question 2. Which of the 4 substances, which of these 4 compounds has the highest concentration of silver? And the answer is C. That's because 2.6 times 10 to the negative 4 moles per liter is larger than 1.3 times 10 to the negative 5. Had you just been looking at the KSP values, you would have actually selected choice A, and that would have been incorrect. So we had to actually do different math because of the 1-to-1 ratio versus the 2-to-1 ratio. So hopefully you can see on this slide, it's a side-by-side comparison of what was the setup for the calculation of silver in AgCl versus what was the setup for the concentration of silver in Ag2CO3. So the correct answer to question 2, based on that higher value of silver ion in solution, is actually choice C. All right, well, hopefully that calculation and that explanation makes sense. Now it's time to move on to our next question in this packet. This is question 3. In question 3, it says that the molar solubility of calcium fluoride, which has the chemical formula CaF2, the molar solubility of calcium fluoride in distilled water at 25 degrees Celsius is equal to 2.1 times 10 to the negative 4 moles per liter. Now, based on this information, a student performs the following calculation to determine the value of KSP for calcium fluoride at 25 degrees Celsius. So here is the student's setup. We can see concentration of the calcium ion times concentration of the fluoride ion squared. They plugged in 2 different values and they did the math and they got 9.3 times 10 to the negative 12. Now in part A it says that the student's calculated value of KSP is incorrect because their value for the concentration of the fluoride ion, F-, is incorrect. So what is the correct value for the concentration of the fluoride ion in a saturated solution of calcium fluoride at 25 degrees Celsius? Now, considering that in question 2 of this packet, we were talking about a 2-to-1 ratio between ions, hopefully you can see that it's the stoichiometry that was the part of what the student did incorrectly in the setup for their calculation. They didn't take into account the stoichiometry and that 2-to-1 ratio of ions. So take a look at the chemical formula of calcium fluoride. You can see that there's the solid on the left, and then we have the aqueous ions on the right. Notice that for every X moles of calcium fluoride that dissolves in water, we get X moles of calcium ions, but then based on that 2-to-1 ratio, we would get twice as much. We would get 2X moles of fluoride ions. And the student didn't actually take that part into account. So if we have 2.1 times 10 to the negative 4 moles per liter for the solubility of calcium fluoride, then that would also be the concentration of the calcium ion. 2.1 times 10 to the negative 4 moles per liter. But we need twice as much for the number of moles of fluoride, so that would be not 2.1, but rather double that. So 4.2 times 10 to the negative 4 moles per liter, that is the answer to part A. The concentration of fluoride should be 4.2 times 10 to the negative 4 moles per liter. Well, now that we've done that, let's go ahead and finish up question 3. It says, in part B, based on the given information and your answer to part A, determine the correct value of KSP for calcium fluoride at 25 degrees Celsius. Let's go ahead and finish off this calculation correctly. It would be concentration of calcium, so 2.1 times 10 to the negative 4, times the concentration of fluoride squared, so times 4.2 times 10 to the negative 4 squared. And if we do this, the correct setup for the calculation, and we do this on our calculator, here's what we get. The correct KSP value should be the following: 3.7 times 10 to the negative 11, and again, there are no units for the equilibrium constant, so there is the correct answer with the correct setup to part B. All right, well, hopefully those answers to parts A and B of question 3 make sense to you. Now, let's move on to question 4 in this packet. In question 4, we can see a diagram that shows an experimental setup. It looks like two different solutions are about to be combined together. It says, a student combines 25.00 milliliters of 9.25 times 10 to the negative 6 molar, and that is nickel nitrate. So nickel nitrate has the chemical formula Ni and then NO3 inside parentheses times 2. So the solution in beaker 1 represents 25.00 milliliters of 9.25 times 10 to the negative 6 molar nickel nitrate. Now there's a different solution in beaker 2. So it's being combined with 45.00 milliliters of 3.20 times 10 to the negative 6 molar sodium hydroxide, which has the chemical formula NaOH. Now they are about to be combined in beaker 3. So part A of this question says the following: calculate the concentration of the nickel 2+ ions after the two solutions are combined in beaker 3, but before any reaction takes place. Assume that volumes are additive. That just means that 25 plus 45 would equal the total volume of the solution in beaker 3. Now, there are two different setups for the calculation in part A. I'm going to show you two different setups that would lead you to the correct answer for part A. So here's the first setup that I will use. So first, we can focus our attention on the solution in beaker 1. And we can calculate the number of moles of nickel 2+ ions that are present in beaker 1. So that would be volume times molarity equals moles. So the volume in units of liters times the molarity, which is moles per liter, that would give us the number of moles of nickel 2+ ions. Now, when I convert from milliliters to liters, I divide by 1,000. So on my calculator or in your head, just by moving the decimal 3 spaces to the left, 25 divided by 1,000 becomes 0.02500 liters. Now, if I multiply by the molarity, which would be moles per liter, that would be, as a conversion factor, times 9.25 times 10 to the negative 6 moles of this nickel nitrate solution for every 1 liter of solution. Now, you don't see in the chemical formula any subscript for the nickel. So just to confirm that there's 1 mole of nickel 2+ ions for every 1 mole of nickel nitrate, I showed that as a conversion factor just to be complete. So if I pick up my calculator, 0.02500 times 9.25 times 10 to the negative 6, this is what I get on my calculator. Now, this is not the final answer to part A, but it's the number of moles of nickel 2+ ions. I got 2.31 times 10 to the negative 7 moles. Of course, the total volume would be 25 plus 45. So 25 plus 45 is 70. And again, it says assume that volumes are additive. So I'm going to take the number of moles of nickel 2+ ions and divide by the total volume in beaker 3. And that would be 70 milliliters, or 0.070000 liters. So we can now take the value for the concentration of nickel by taking number of moles divided by volume in liters. So this is what I did to get the answer to part A. I did 2.31 times 10 to the negative 7 moles divided by the volume in liters, and that would be 0.07. And when I did that math, this is the correct answer to part A. 3.30 times 10 to the negative 6 moles per liter, that is the concentration of nickel 2+ ions in beaker 3 after the two solutions are combined. Now, if you're watching this video and you're saying, Mr. Farabaugh, I did a different calculation than you did, but I got the same answer that you did, I'm going to show you that alternate method of calculating the concentration of the nickel 2 plus ions in beaker 3. And that would be what I call the dilution equation. So it's written as M times V equals M times V, where the M is molarity and the V is volume. Now, if you do M times V equals M times V, you will get the same answer. And note that these two volumes don't have to be in liters. They could be in milliliters as long as they are the same on both sides of the equation. So here is an alternate setup to give us the same answer to part A. So M times V equals M times V. What's the molarity of the nickel solution in beaker 1? Well, that would be 9.25 times 10 to the negative 6 moles per liter. So I will put that for my M1. Now, what's my volume? Well, that would be 25 milliliters. I'm going to go ahead and leave the volume in units of milliliters. What's my M2, or my new molarity? Well, let's pretend that we don't know what that value is yet. So I will just call that a question mark. And the new volume would be 70 milliliters. So we should get the same answer that I showed you earlier, but now the calculation would look like this. Let's solve for the question mark, or the unknown concentration of the nickel 2 plus ion in beaker 3 by doing 9.25 times 10 to the negative 6 times 25 and then divided by 70. And if you do that math, yes, you do get the same answer that I had mentioned earlier, which is concentration of the nickel 2 plus ion in beaker 3 is 3.30 times 10 to the negative 6 moles per liter. So if you prefer, you could calculate the number of moles, divide by the total volume in liters, and you could also use the M times V equals M times V setup, and there is your answer to part A. 3.30 times 10 to the negative 6 moles per liter. Now, there's going to be a precipitate possibly formed in beaker 3, and I say possibly because we have to do a Q versus K comparison, so that's coming up in the next few parts of this question. Let's go ahead and move on to part B of question 4. So there is our answer to part A, just so we have a chance to make a note of that. So part B talks about the dissolution of a substance known as nickel Roman numeral 2 hydroxide. So nickel Roman numeral 2 hydroxide has the following chemical formula. Ni, and then OH in parentheses times 2. That's a solid on the left, and then there's the aqueous ions on the right. So what you're seeing is the dissolution of nickel hydroxide with a KSP of 5.48 times 10 to the negative 16. So what do we have to do in part B? We don't have to do a calculation. All we have to do is write the expression for the solubility product constant, KSP, for this nickel hydroxide compound. Now, the answer to part B of question 4 looks very similar to the answer to part A of question 1 in this packet. So it's going to be that similar setup with that 1:2 ratio like we saw in part A of question 1. So it's concentration of nickel times concentration of hydroxide squared. Now, there is a calculation that we have to do in part C, and it's going to be called the reaction quotient. So here's part C. After the two solutions are combined in beaker 3 as described above, but before any reaction takes place, the concentration of the hydroxide ion in beaker 3 is 2.06 times 10 to the negative 6 moles per liter. So using your answer to part A, calculate the value of the reaction quotient Q. So I'm going to put in 2.06 times 10 to the negative 6 moles per liter for the concentration of hydroxide, and that is squared based on our answer to part B. And then what do I do for the concentration of nickel? Well, that was our answer to part A. So it's 3.30 times 10 to the negative 6 moles per liter. Now, let me pause for just a moment. Some of you watching this video might be a little bit confused or concerned. You might be thinking, shouldn't there be a 1:2 ratio of nickel to hydroxide? And the answer is not necessarily in this case, because they came from two separate solutions. So what I'm showing you on this slide are correct numbers for this calculation. But it says here at the bottom of the slide, note that these two values are not in a 1:2 mole ratio because each ion, the nickel ion in beaker 1 and the hydroxide ion present in beaker 2, they came from separate solutions, different concentrations. So that's why we don't need that 1:2 ratio. So the nickel came from nickel nitrate, the hydroxide came from sodium hydroxide, two separate solutions, separate concentrations. All right, when I pick up my calculator, I did 3.30 times 10 to the negative 6 times 2.06 times 10 to the negative 6 squared, and this is what I got. Now, this is Q. This is not K. This is simply the reaction quotient Q, which is what we have in beaker 3 at the moment that those two solutions are combined. So if you're wondering, what do I do with 1.40 times 10 to the negative 17? It's going to be a Q versus K comparison. Now, in an earlier episode of AP Chemistry Review and Practice, which was episode 21, I had talked about topic 7.7, which involves a Q versus K comparison. So we are about to do a Q versus K comparison as we move from part C of this question to part D. Let's take a look at part D. It says, using the reaction quotient Q, which we have in part C, predict whether a precipitate should form as the mixture in beaker 3 approaches equilibrium. Justify your answer. Now that justification will be, is Q larger or smaller than K? That's going to be part of our justification in part D. So in an earlier episode of AP Chemistry Review and Practice, I talked about topic 7.7, and let me go ahead and show you the Q versus K comparison. When Q, the reaction quotient, is less than K, the equilibrium constant, the reaction will proceed from left to right with a net consumption of reactants and generation of products. So if this is our equilibrium for the dissolution of nickel hydroxide, and if QSP is less than KSP, a precipitate will not form. Why? Because there is a net conversion from left to right, and the equilibrium favors the formation of the aqueous ions, so no precipitate would form. But on the other hand, if Q is greater than K, then the reaction would proceed with a net consumption of products and generation of reactants, so from right to left. So if QSP is greater than KSP, then yes, a precipitate will form, because now, with a net conversion from right to left, the equilibrium favors the formation of the solid, and a precipitate will form. Let's go ahead and do our comparison of Q versus K in this question. So as we compare the value of QSP with the value of KSP, we learn that 1.40 times 10 to the negative 17, which is our version of Q, is in fact less than KSP, which is 5.48 times 10 to the negative 16. And so when the value of Q is less than the value of K, a precipitate should not form. So I have answered part D. Should a precipitate form? No, because the value of Q is less than the value of KSP. All right, well, hopefully all of those answers and explanations to question 4 make sense to you. Now, it is time to move on to question 5 in this packet, and this is a multiple choice question. Now, as I look at the details of question 5, specifically the 4 answer choices, I can see that just like the last part of question 4, we're going to have to do a Q versus K comparison in order to predict whether or not a precipitate will form. So let's go ahead and read the details of question 5. It starts off by saying that a 1 liter solution of barium nitrate, which has the chemical formula Ba and then NO3 in parentheses times 2, a 1 liter solution of barium nitrate has a barium 2+ ion concentration of 1.0 times 10 to the negative 6 moles per liter. So I'm showing you a beaker with 1 liter of solution, and the concentration of the barium 2+ ion is 1.0 times 10 to the negative 6 moles per liter. Now they're going to add something to this beaker, and they're adding a 0.0010 mole sample of solid potassium sulfate. Now, potassium ions are part of that set of soluble ions that I had mentioned earlier: sodium, potassium, ammonium, and nitrate. So when the potassium sulfate goes into this solution, it will dissolve, producing potassium ions and sulfate ions. So it says the solution is stirred to ensure that it's thoroughly mixed. So now we're at this stage where we have 1 liter. It says assume that the volume of change of the solution is negligible. So 1 liter of solution, we know the concentration of barium, and because 0.0010 mole of potassium sulfate is added, that also would be the number of moles of sulfate present in a 1 liter solution. So my concentration of sulfate is 0.0010, or in scientific notation, that would be 1.0 times 10 to the negative 3 moles per liter. So it's going to be a Q versus K comparison. The value of KSP for barium sulfate is 1.08 times 10 to the negative 10. It says, which of the following will occur and why? So will a precipitate form, yes or no? And it's going to be either because Q is less than or greater than KSP. So here is the equation for the dissolution of solid barium sulfate. You can see solid barium sulfate on the left and the aqueous ions, barium and sulfate, on the right. And so we have concentration of barium times concentration of sulfate in our KSP. But let's go ahead and do Q. So at the moment that this beaker exists, we don't know for sure if there is going to be a precipitate of barium sulfate until we do a Q versus K comparison. So what's the concentration of barium in this beaker? It's 1.0 times 10 to the negative 6 moles per liter. What's the concentration of the sulfate ions in this beaker? Well, that would be 1.0 times 10 to the negative 3 moles per liter. And if we multiply these two values together, this will give us the reaction quotient Q. And that works out to be 1.0 times 10 to the negative 9. Now, since that number, 1.0 times 10 to the negative 9, happens to be greater than the value of KSP, we can go ahead and make our prediction based on the fact that Q is greater than K. So as I had mentioned earlier, when Q is greater than K, there will be a net conversion from right to left, as in from products to reactants. So if QSP is greater than KSP, then yes, a precipitate will form because the equilibrium favors the formation of the solid. So the correct answer to question 5 is choice A. Barium sulfate will precipitate because Q is greater than KSP. All right, well, hopefully that particular answer and explanation makes sense to question 5. It's now time to move on to question 6, which is also a multiple choice question. In question 6, we are given a balanced chemical equation for the dissolution of solid calcium carbonate, which has the chemical formula CaCO3. We are also given a diagram representing an experiment. Before we look at the 4 answer choices for question 6, let's go ahead and take a look at the details of this experiment. It says the dissolution of calcium carbonate, so CaCO3, is represented by the equation shown above. A student prepares a 50 milliliter sample of a saturated solution of calcium carbonate at 25 degrees Celsius by adding excess solid calcium carbonate to distilled water and stirring until no more solid dissolves. So that would be the beaker on the left side of the diagram. And this is a saturated solution. Again, you can see undissolved solid at the bottom of the beaker in that diagram. Now, the next thing that occurs is after about 30 minutes, the student adds additional distilled water to the beaker and stirs the mixture thoroughly until no more solid dissolves. And as you can see, a small amount of undissolved solid calcium carbonate is present at the bottom of the beaker on the right side of this diagram. So it's important to realize that this is still a saturated solution. Did all of the solid calcium carbonate dissolve? No. And so because it remains saturated, that's going to be an important part of how we determine the correct answer to question 6. Now, you don't need to do a calculation to answer question 6, but I'm going to go ahead and do a calculation just to show you how you would determine the concentration of the calcium ion in a saturated solution of calcium carbonate by taking the square root of the KSP value. So based on this 1-to-1 mole ratio between calcium and carbonate, that would be x times x, or x squared. And so to solve for x, you take the square root of 3.36 times 10 to the negative 9, which is the KSP. So the concentration of calcium in this saturated solution that was made by dissolving the solid in water is 5.8 times 10 to the negative 5 moles per liter. And that's not only the concentration of calcium in the beaker on the left side of the diagram, it's also the concentration of calcium on the beaker in the beaker on the right side of the diagram. So because each of these solutions, the 50 milliliter sample and the 100 milliliter sample, are saturated, each solution has the same concentration of calcium ions in it. So what you can see is that we now have the question and 4 answer choices. It says, which of the following provides correct comparisons of both the concentration of calcium, which is the first column, and the number of moles of aqueous calcium ions, which is the second column. So we're comparing the 50 milliliter sample of solution before the additional water was added and the 100 milliliter sample of solution after the water was added. But each solution is saturated, so each solution has the same concentration of calcium ions. And so that means that the correct answer to question 6 is either choice C or D. So not less than, but the same as is the correct comparison for the concentration of the calcium ion. So I'm going to eliminate choices A and B, and now we have to determine, is the correct answer C or D? Let's compare the number of moles of calcium ions in these two samples of solution. Now, as you know, molarity is moles per liter, and although we have the same concentration, which would be moles per liter, we have a different volume. So the 100 milliliter sample, because it contains a larger volume of solution at the same concentration, it should contain a greater number of moles of calcium ions. So that makes the correct answer to question 6, choice C. Same concentration of calcium as the 50 ml sample, but a greater number of moles of calcium ions as compared to the 50 milliliter sample. All right, well, hopefully that answer and explanation makes sense. Now, this is question 6. Before we take a look at question 7 in the packet, we're about to move to our next topic. So it's now time to move on to the review for topic 7.12, a very brief essential knowledge statement for topic 7.12, common ion effect. It says, the solubility of a salt is reduced when it is dissolved into a solution that already contains one of the ions present in the salt. The impact of this common ion effect on solubility can be understood qualitatively using Le Chatelier's principle or calculated from the KSP for the dissolution process. Now it's time to move on to the practice for topic 7.12. This is question 7. Now, question 7 is a multiple choice question, but before we consider the 4 answer choices, let's consider the details of the experiment in question 7. It says that lead Roman numeral 2 iodide, which has the chemical formula PbI2, dissolves in water according to the following equation. And we are told that a student prepares a saturated solution of lead iodide by adding excess solid lead iodide to distilled water at 25 degrees Celsius and stirring until no more solid dissolves. Now that procedure is very similar to what was described in question 6 for making a saturated solution of calcium carbonate. It says that the saturated solution is in beaker X. That's on the left side of the diagram, and that was prepared by adding excess solid lead iodide to water. The student determines that the concentration of lead is 0.0013 molar in this solution, which again is labeled as beaker X in the diagram below on the left. Now you might be wondering, what's the concentration of iodide in beaker X? Based on that 1:2 ratio as shown in the balanced chemical equation, there should be twice as many moles of iodide in that solution in beaker X. So I'll say that 0.0013 times 2 would be 0.0026 molar for the concentration of the iodide in beaker X based on the 2:1 mole ratio. Now, as we move on to beaker Y, this is an example of what is called the common ion effect. What happens if you try to dissolve lead iodide into a solution that already contains a common ion? So the next part of the question says, the student prepares a second saturated solution of lead iodide, but they're not dissolving it in water. They're dissolving it in a solution that already contains a common ion. So the saturated solution in beaker Y on the right was prepared by adding excess solid lead iodide to a solution of 0.10 molar potassium iodide. Now, 0.0026 molar was the concentration of the iodide in beaker X. But now we have a much higher concentration of iodide. Why? Because it was already there in the form of potassium iodide. So we already have a 0.10 molar concentration of potassium iodide before the lead iodide was added to create the solution in beaker Y. So again, the common ion effect says that the solubility of a salt is reduced when it is dissolved into a solution that already contains one of the ions present. So there's my equation for the dissolution of solid lead iodide, but the presence of a common ion, in this case, for example, dissolving a sample of lead iodide into a solution that already contains iodide ions, that should cause the value of QSP to be greater than the value of KSP. So why is Q greater than K? Because of the extra iodide ions present from this outside source, the potassium iodide. So that will cause a net conversion from products to reactants or from right to left. And by favoring the formation of the solid, that makes lead iodide less soluble in a solution that already contains a common ion. So we are predicting, based on the fact that Q is greater than K, that's because of the extra iodide ions from that potassium iodide solution that was already present, to create a net conversion from right to left, or favoring the formation of the solid, making it less soluble. So before I look at the 4 answer choices, I wanted to show you that based on these details and our understanding of the common ion effect in topic 7.12, our prediction is that in beaker Y, the concentration of the lead ion in solution should be less than 0.0013 molar. So looking at the 4 answer choices, it's going to be not equal to, but rather less than, and that's based on this information, which of the following provides the correct predictions for both the value of the concentration of lead and the value of KSP in beaker Y. So I'm looking for less than, not equal to. So I will go ahead and eliminate choices C and D, and that's because if Q is greater than KSP, and there should be a smaller concentration of lead in beaker Y compared to beaker X, then it's not equal to, it's less than. Okay, so we're almost done answering this question. We know it's either A or B. What about the value of KSP? Is that going to be affected? So in an earlier episode of AP Chemistry Review and Practice, I talked about the value of the equilibrium constant as it relates to changing the temperature. And so in this case, it says assuming that the temperature remains constant at 25 degrees Celsius. Well, back in an earlier episode of AP Chemistry Review and Practice, a change in temperature does cause the value of K to change, but that also means that if the temperature remains constant, the value of K remains constant. So if the temperature remains constant, the value of the equilibrium constant remains constant, and so therefore the value of KSP should not change because the temperature remains constant in this experiment. So the correct answer to question 7 is choice B. Based on the common ion effect and the extra iodide ions present in beaker Y, we would predict that the lead iodide would be less soluble in a solution that contains a common ion. So that's why the concentration of lead would be less than 0.0013. But with no change in temperature, the value of KSP remains the same. All right, well, that is the answer to question 7, and now it's time to move on to question 8. Question 8 says the following. The dissolution of the slightly soluble salt, calcium phosphate, is represented by the equation above. So we can see solid calcium phosphate on the left, and we can see the ions, the calcium ions and the phosphate ions on the right. It says, which of the following changes will decrease the concentration of the calcium ion in a saturated solution of calcium phosphate, and why? Assume that after each change, some solid calcium phosphate remains in contact with the solution. So what we are doing to determine the correct answer to question 8 is we're asking ourselves the following question. Which of the following changes would result in a net conversion for this equilibrium from products to reactants, or from right to left, favoring the formation of the solid and decreasing the concentration of the calcium ion in the solution? So I'll start with choice A and then work my way down to choice D. So choice A says the following: adding solid calcium phosphate, because the value of Q will become greater than the value of K. Now, we already know that solids are not included in the equilibrium constant expression, so therefore, if we added additional solid to a saturated solution, this has no effect on the value of the reaction quotient Q. So solid calcium phosphate does not appear in the KSP expression. Adding more solid should have no effect, so we can eliminate choice A. Now, moving on to choice B, they added a substance which is not calcium phosphate, but a substance that contains a common ion. So they're adding solid potassium phosphate. Now, potassium is one of those sets of soluble ions. So there's sodium, potassium, ammonium, and nitrate. So they're adding additional solid potassium phosphate. Salts that contain potassium ions should be soluble in water. And so if we add some potassium phosphate to this saturated solution, it will result in a slight increase in the concentration of the phosphate ions. So we're adding potassium phosphate to the saturated solution. Phosphate ion concentration goes up. Q should become greater than K, as in QSP should be greater than KSP, because the concentration of phosphate is increasing. And there should be a net conversion from right to left. And yes, this would cause the concentration of the calcium ion in solution to decrease. So I like choice B because of the common ion effect. Calcium phosphate should be less soluble in a solution that contains an additional amount of a common ion, in this case, the phosphate ion. Now let's go ahead and just make sure that choice B is correct. So I will still consider choices C and D just to make sure that they are not the correct answer. So moving on to choice C. Choice C says allowing some of the water to evaporate from the solution because more solid calcium phosphate will precipitate. So if you have a saturated solution and you evaporate some of the water, well, this would increase both ions concentration. So if you remove some water by evaporation, both ions would increase. At that moment, that would cause Q to become greater than KSP, but then to return to equilibrium and to reestablish equilibrium, then additional solid would precipitate, equilibrium would be reestablished, and Q would remain equal to K once equilibrium is reestablished. You'd have a saturated solution, but you were not adding any additional substances, so you would return to the same concentrations as before. The concentration of both the calcium and the phosphate, they would go up, and then they would return to their original values for the saturated solution, so they would both remain the same. That's why we can eliminate choice C. And then finally, choice D says if we added additional 0.1 molar potassium nitrate, well, that would cause the additional liquid to dilute the solution, and they're suggesting it would decrease the concentration of the calcium. But again, that last part of the sentence says, assume that after each change, some solid calcium phosphate remains in contact with the solution. It remains saturated. If they added a little bit of this 0.1 molar potassium nitrate, the excess solid would still be present at the bottom of the beaker. It would remain saturated. Q equals K. We did not change the concentration of calcium or phosphate because we still have a saturated solution, and potassium and nitrate, those are not common ions. So correct answer is definitely choice B. Okay, so what does this have to do with the common ion effect? The solubility of a salt is reduced when there is a common ion present. So what's the common ion? That would be the fact that we're adding more phosphate ions. So increasing the concentration of that common ion, adding more phosphate ions to a saturated calcium phosphate solution, that would cause Q to be greater than KSP. There would be a net conversion from right to left, decreasing the concentration of the calcium ions. So that's why choice B was the correct answer to question 8. All right, we have one more example of another situation involving the common ion effect. So topic 7.12, this is question 9. Question 9 says the following. The value of KSP for magnesium fluoride, or MgF2, at 25 degrees Celsius is 5.16 times 10 to the negative 11. Now note, you can take a look at the 4 answer choices in question 9 and you can realize this will be a calculation question. So we will plug the KSP value for magnesium fluoride into our calculator at some point. It goes on to say that a chemist prepares a saturated solution at 25 degrees Celsius by adding excess solid magnesium fluoride to, notice it's not pure water that they're dissolving the solid magnesium fluoride into. They're dissolving it into a solution of aqueous sodium fluoride of unknown concentration. So again, there's the example of the common ion effect. Magnesium fluoride should be less soluble in a solution that already contains, in this case, the common ion fluoride. It goes on to say that the mixture is stirred until no more solid dissolves, and the value of the concentration of magnesium in the saturated solution is equal to 3.23 times 10 to the negative 10 moles per liter. Again, this will be a calculation question, so we will need to do something with these two numerical values. Now, before I continue talking about how to set up the calculation, I'd like to show you what would happen if we dissolved the magnesium fluoride into water, as opposed to dissolving the magnesium fluoride in a solution that contains a common ion. So I'm going to take a break from this question and remind you of something I had presented earlier in this lesson. So earlier in this lesson, I was talking about the KSP for silver carbonate, Ag2CO3, and it was a 2-to-1 ratio of silver to carbonate. And so when I set up that calculation, it was 2x quantity squared times x equals 4x cubed, and then I proceeded to set up the calculation to solve for the concentration of the silver. Now, we also have a 2-to-1 ratio, in this case, 2 moles of fluorine or fluoride ion for every 1 mole of the magnesium ion. So it's going to be a similar setup. That's why I'm presenting it as a companion to the calculation I had presented earlier. So x could represent the concentration of magnesium, 2x could represent the concentration of fluoride, and again, let's assume that we dissolved the magnesium fluoride into pure water and not a solution that contains a common ion. So let's see, what would the concentration of magnesium be if we prepared a saturated solution by dissolving magnesium fluoride in pure water? So it would be x times the quantity 2x squared. So there's that 4x cubed again. This time we will take the KSP for magnesium fluoride. We will divide by 4 and then take the cube root. So divide by 4, take the cube root. That will help us solve for x. And when I do that math, 5.16 times 10 to the negative 11, divide by 4, take the cube root, I get 2.35 times 10 to the negative 4 moles per liter. So that number that you're seeing on the bottom left corner of this slide, that is the concentration of magnesium that would be present in a saturated solution of magnesium fluoride if we had dissolved it in pure water at the start. Now let's go back and compare what I'm just showing you now with what it said in question 9. So 3.23 times 10 to the negative 10, that is much, much smaller than what I just got. So again, this is the common ion effect. Note that the value of the concentration of magnesium in this solution that had sodium fluoride already present, that is much less than what the concentration of magnesium would have been if we had started by dissolving this solid in pure water. So again, that's the common ion effect. Additional fluoride ions were present in that beaker in the form of sodium fluoride before the magnesium fluoride was added. So magnesium fluoride is much less soluble in a solution that already contains a common ion, the common ion being fluoride. Okay, now back to this particular question, and let's go ahead and do the calculation to finish question 9. So here is my KSP. What's the concentration of magnesium? We were given in this question, it was 3.23 times 10 to the negative 10. What's the concentration of the fluoride ion? That's what we're trying to answer in question 9. What's the value of KSP? 5.16 times 10 to the negative 11. So looking at the setup for this calculation, the only thing that we don't know at the moment is the concentration of the fluoride ion that would be present in the beaker in this diagram shown above. So I will go ahead and divide both sides of the equation by 3.23 times 10 to the negative 10. So now I have concentration of fluoride squared is equal to 0.16 when I did that on my calculator. Let's go ahead and take the square root of 0.16, and when I do that calculation, I get that the concentration of fluoride is equal to the square root of 0.16, or 0.40 molar. So we have now answered question 9 by plugging in the concentration of the magnesium ion that we were given, and also knowing the value of KSP, and then solving for the concentration of the fluoride ion. So 0.40 molar is the correct answer to question 9, and that makes choice D the correct answer to question 9. So again, the message about the common ion effect is that magnesium fluoride is much less soluble in a solution that already contains fluoride ions. All right, well, since question 9 was the last question in this packet, now we have come to the part of the lesson where I give you advice to help you avoid common mistakes. So my first piece of advice is if you need more information or more practice problems for these two topics, you can review the information in my video for topics 7.11 and 7.12, and you'll find a link to that video in the video description area. My next piece of advice is what I normally say during this part of the lesson, and that is to read the question carefully and make sure you are answering the question that is being asked. Always show your work for your calculations, and when setting up a calculation involving either QSP or KSP, take care to avoid errors with arithmetic or algebraic manipulations. For example, solving for x in an equation involving KSP equals 4x cubed, and then remembering to divide by 4 and take the cube root and doing that correctly. Now, if you need to write a balanced chemical equation for the dissolution of an ionic solid in water, such as the example shown above for magnesium phosphate, remember the following guidelines. Phases of matter are not normally required to earn the point for your answer on the AP Chemistry exam. However, it might be a good idea in these types of questions to include the phases of matter for the dissolution of an ionic solid because it reminds you that solids are not included in the KSP expression. Also, water, H2O, is not included in these types of dissolution chemical equations. Make sure to include the correct charges on the aqueous ions, which appear on the right side of the equation. Make sure that the overall equation is balanced in terms of atoms and charge. The stoichiometry of the balanced equation for the dissolution of an ionic compound is important. The molar solubility of an ionic compound is not the same as the KSP value for the compound. And the molar solubility of an ionic compound will not necessarily be the same as the concentration of each aqueous ion in the solution. So let's go ahead and consider this example, which is calcium hydroxide. Calcium hydroxide dissolves in water to produce the ions calcium and hydroxide, and you can see the balanced equation, the KSP, and you can also see two different units for solubility in this table. So the solubility of an ionic compound can be reported with units of moles per liter or grams per liter. And you can use the molar mass of the compound in order to convert from one of these units into the other. So, for example, there's the calculation for the molar mass of calcium hydroxide, which is 74.096 grams per mole. If you were given in an AP chemistry question that the solubility of calcium hydroxide was 0.800 grams of calcium hydroxide per liter, then you could use the molar mass, converting from grams to moles, and if you set up that calculation correctly, then 0.8 divided by the molar mass would give you 0.0 108, and now it has units of moles per liter. You could also go in the opposite direction. If you were given the molar solubility of calcium hydroxide, then you would use the molar mass and the conversion factor to go from moles to grams, and you would obtain the solubility of calcium hydroxide in units of grams per liter. And you can see in the table that 0.0108, that happens to be the concentration of calcium. But notice that the concentration of hydroxide is not 0.0108. It's twice as much because of the stoichiometry. So that's why the concentration of the hydroxide ion in this saturated solution would be twice as much as the concentration of the calcium ion in this saturated solution. My next piece of advice is that there is an important difference between molarity, moles per liter, and the number of moles, as we saw in question 6 in this lesson. My next piece of advice is that a saturated solution of an ionic solid can be prepared by adding an excess amount of an ionic solid to a sample of distilled water and stirring the mixture until no more solid dissolves. So if you see a diagram or a picture of a beaker or a flask, the presence of undissolved solid at the bottom of the container is a visual indication that the solution is, in fact, saturated. Now, the table on the next page lists examples of different ionic compounds along with their KSP values. So the concentrations of the aqueous ions in a saturated solution can be calculated from the KSP value. Now let's assume that each saturated solution was prepared by dissolving the solid in distilled water. You'll notice I have a 1-to-1 ratio of cations to anions in AgCl. And then the next two examples, I have a 2-to-1 or a 1-to-2 ratio of cations to anions. And then I've got two more examples. I've got a 1-to-3 ratio and then finally a 3-to-2 ratio. I'm going to go ahead and show you the math to make sure that you can go from the KSP to the molar solubility of the ions. So I'll start with the simplest example, which is the 1-to-1 ratio of the cations and anions in AgCl. All we have to do to determine the concentration of each ion is take the square root of the KSP value. And when I take the square root of the KSP, I get 1.33 times 10 to the negative 5, which is not only the concentration of the silver ion, but also the concentration of the chloride ion in this saturated solution. Now, our next two examples have a 1-to-2 or a 2-to-1 ratio. Let's take a look. So here is the Ag2CO3. So it's going to be a 2-to-1 ratio of silver to carbonate. So that's why it's not x squared, it's 2x quantity squared times x, and I get 4x cubed. That would be divide the KSP value by 4, and then take the cube root. And if I did that, if I divided by 4 and take the cube root, that would get me the x, or the concentration of the carbonate ion. So that was 1.28 times 10 to the negative 4 molar when I did that math. So what's the concentration of the silver ion? 2x, or twice as much, so that's 2.56 times 10 to the negative 4 moles per liter. Our next example is also a 2-to-1 ratio. This time it's barium fluoride. So again, there's the x for barium and the 2x for fluoride, but that's 2x quantity squared. There's that 4x cubed again. Divide the KSP by 4, take the cube root, and so 3.58 times 10 to the negative 3 molar is what I did on my calculator to get that answer, and that's the concentration of barium. And the fluoride would be twice as much, or 7.16 times 10 to the negative 3 molar. Now, our next two examples are different than what we've seen in this lesson. So here is iron, Roman numeral 3 hydroxide, which is Fe, and then OH in parentheses times 3. So because it's a 1-to-3 ratio, it was x for iron, 3x for the hydroxide, and then cubed, or raised to the third power. So I got 27x to the fourth power is equal to my KSP. Now I had to divide by 27 and then take the fourth root. You can also just raise that quantity to the 1/4 power on your calculator as opposed to finding some fourth root button. So I could take 2.79 times 10 to the negative 39, which is the KSP, divide by 27, and then I would take that quantity and raise it to the 1/4 power. So when I did that, I got the concentration of iron was 1.01 times 10 to the negative 10 molar, and then the hydroxide concentration would be 3 times as much. So you can see 3.03 times 10 to the negative 10 molar for the concentration of the hydroxide ion. And then one final example in this table was also kind of challenging with respect to the math and the ratios. It was 3 calciums and 2 phosphates. So they were in a proportion of 3x for the concentration of the calcium ion, 2x for the concentration of the phosphate ion, but I had to still raise it to the appropriate power based on the coefficients. So when I did 3x quantity cubed and 2x quantity squared, I got 108 times x to the 5th power. So how did I solve for x? I divided by 108 and then I raised it to the 1/5 power and I got my x. Now the concentration of phosphate would be 2x, which is why I multiplied 1.14 times 10 to the negative 7 by 2. And then I multiplied that x by 3 to get the concentration of calcium. So I just wanted to show you that if you're given the KSP, you could determine the concentration of each aqueous ion by doing the appropriate math. So now you can see several examples of different ionic compounds and different ratios and how to do that math. All right, my next piece of advice is suppose that you are given the KSP values for 2 different ionic compounds, but they have the same ratio of cations to anions. For example, calcium fluoride is CaF2 and barium fluoride is BaF2. Well, if you compare the KSP values, then you can say the compound with the higher KSP value does in fact have the higher value for its molar solubility. On the other hand, what if you are given the KSP values for 2 different ionic compounds, but they don't have the same ratio of cations to anions? So for example, silver chloride is AgCl, silver carbonate is Ag2CO3. Well, as I showed you earlier in this lesson, you would need to do the calculations for each compound in order to determine the concentration. So again, that would be sometimes just take the square root if it's a 1-to-1 ratio, but other times you may have to divide by 4 and take the cube root if it happened to be that 4x cubed that I showed you earlier. My next piece of advice is that sometimes you have to predict whether or not a precipitate will form when solutions are combined. So we saw this in question 4 in this packet. So the best strategy is to do a comparison of QSP versus KSP as we saw earlier in this lesson. Calculate the concentration of each ion present in the solution after these 2 solutions have been combined, but before any reaction takes place. So that would get you Q. Use the concentration of each ion and calculate the value of the reaction quotient Q. Now, if the value of Q is less than KSP, a precipitate will not form because the equilibrium favors the formation of the aqueous ions on the right side of the equation. But if the value of QSP is greater than KSP, then yes, a precipitate will form because now the equilibrium would favor the formation of the solid on the left side of the equation. Now, my next piece of advice is there's another situation that involves a comparison of Q versus K, and that's topic 7.12, the common ion effect. So again, the presence of a common ion, for example, dissolving a sample of silver chloride into a solution that already contains chloride ions, that should cause the value of Q to be greater than KSP. And so as a result, the salt becomes less soluble in a solution that already contains a certain amount of a common ion. So the equilibrium would experience a net conversion from the right to left, or from products to reactants, favoring the formation of the solid, making it less soluble. And then finally, you can plug in the known value for the concentration of one ion into the KSP expression, and then you can do the calculation to determine the concentration of the other ion in solution. And we did that in question 9 in this packet. All right, so now we have come to the end of this lesson. In my next lesson, I'll give you the chance to review and practice topics 8.1 to 8.3. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which include the link to my YouTube playlist organized by AP Chemistry CED units. You can add your comments and questions below this video, And you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.